Hello everyone, my name is Kazi and I'm a PhD candidate at the Department of Civil Engineering at UT Arlington. Today I will be talking about the experimental investigation of vortex-induced forces on submerged bridge decks and vortex-induced scour around cylindrical piers subject to different flow conditions. Here is the outline of my presentation. I will begin with the introduction and motivation for selecting this topic. Then I will present my objectives followed by the plans to fulfill those objectives. I have divided my presentation into two major sections. In the first section, I will be talking about the vortex-induced forces on submerged bridge decks, and in the second part, I will talk about the vortex-induced cover around a single cylindrical pier at different flow conditions. And finally, I will summarize the conclusions drawn from this study. So let's start. Bridges are a critical part of any transportation network, yet scour remains one of the leading threats to their structural stability. When bridges are exposed to extreme flood forces, the consequences can be even more severe. Blanco River flood event in 2015 in Texas is one of the disastrous flood event in recent times. The water rose more than 33 feet in 3 hours, cresting about 40 feet or 27 feet above the flood stage. This flood led two bridge collapsed due to high water level at Blanco River that were built to withstand a 100-year flood according to TxDOT. Engineers believe that it was not only the flood water but the scour around the foundations that led the two bridges to fail. This slide gives us more statistical information on the vulnerability of bridges to flood and scour. The first image here shows that between 1989 and 2012, 832 bridges failed in the US. The second figure breaks these down by causes, and we can clearly see that flood and scour are the top two contributors. In fact, more than 50% of those failures were linked to flood and scour. Now, when the flow interacts with a hydraulic structure in a regular or flat condition, a very unique flow pattern is observed around the structure dominated by the creation of flow vortices that cause scour and eventually bridge failures. This presentation will highlight the influence of vortices on flow structure and flow sediment interactions. During a critical river flood event, a bridge may become partially or completely submerged by the flow. The first figure here shows the mean flow field around a rectangular deck in a horizontal plane. The primary separation of the shear layer occurs on the leading edge, which is here. When the reattachment occurs on the downstream side, the flow makes a region of recirculation. In this condition, the secondary separation at the downstream edge causes the roll-up of the flow in the rear phase that generates a secondary vortex. The second figure shows the vortex activities around a submerged deck in the vertical plane. Submergence reduces the effective flow area beneath the deck, causing a significant acceleration of water velocities. This in turn generates steep pressure gradients and powerful flow separation characterized by vortex shading and downward jets that contribute to accelerated scour. Different structural elements of the bridge interact differently with the flow. We have already seen how the flow dynamic around a bridge deck is in a riverine flow condition. This slide shows the flow dynamic around a pier in a riverine condition. Riverine conditions represent current alone cases when there is no waves. In a current alone condition, when the flow meets pier, the main flow features observed are surface rollers, horseshoe vortices, etc. on the upstream side of the pier and wake vortices on the downstream side of the pier. In coastal environments, the waves alone cases are observed. Waves are multidirectional and the wave actions steer up bed materials, and eventually sediment particles are carried away from the vicinity of the pier. The Keulligan-Carpenter or the Kc number is considered one of the main parameters to define scour in flows associated with waves. It is a dimensionless number expressing the relative magnitude of the flow and structure length scales. As we can see, this parameter depends on parameter like maximum wave induced velocity, wave period, and PR diameter. And this maximum wave induced velocity depends on parameters like wave height, wavelength, water depth, etc. Finally, in lacustrine environment, wave and current coexist. Because of their coexistence, the Scour mechanism here is complex. In these cases, waves are more capable of lifting sand and the current is more capable of carrying them. So in this environment, sand is picked up by waves and then transported by the current. The few empirical formula available for Scour depth calculation for these cases includes the parameter UCW, which is the ratio of waves and current components in wave current flows. The value of this parameter varies between 0 to 1. When the UCW value is more than 0.7, the current component is more dominant and the wave has much less effect on the flow. So depending on the unique vortex characteristics around different bridge structural element, this study had two main objectives. Firstly, the investigation of vortex-induced forces on submerged bridge decks. PIV was used to investigate the flow structure around submerged bridge decks in the vertical plane, and then the effect of different bridge geometry and flow parameters on those flow structures and flood forces were investigated. Then the second part was the investigation of vortex-induced scour around cylindrical piers subject to wave and current. Again, PIV was used to investigate the flow structure around a single pier in the horizontal plane. Then the vortex characteristics around the pier was used to justify the size and shape of scour hole developed around the pier at various flow conditions. Let's start with part 1, investigation of vortex-induced forces on submerged bridge decks. These are the definitions of the dimensionless hydraulic and geometric parameters used in the flood force study. The hydraulic parameters include inundation ratio, proximity ratio, and fluid number. The geometric parameters include aspect ratio and blockage ratio. The inundation ratio gives us an idea about the submergence level of the deck. Proximity ratio tells us how close the deck is to the channel bed. Fluid number is the ratio between inertia and gravity force. Aspect ratio is the ratio between deck width and deck thickness. And finally, blockage ratio gives us an idea about how much flow is being blocked by the deck. The flood-induced force on bridges can be divided into hydrostatic and hydrodynamic components. The hydrostatic component includes hydrostatic and buoyant force, and the hydrodynamic force includes drag, lift, force, and overturning moment. Hydrodynamic drag force acts parallel to the flow direction and it pushes the deck off of its piers and substructures. Hydrodynamic lift acts vertically and perpendicular to the flow and can lift the bridge deck off of its piers and abutments. The uneven distribution of the drag and lift causes overturning moment about the center of gravity of the bridge deck, which can cause the bridge deck to overturn. In these equations, CD, CL, and CM are drag force, lift force, and moment coefficients. These non-dimensional values are essential information for designing bridges under flood forces. The study of interaction between flood and bridge superstructure required the understanding of bluff body fluid mechanics. When the flow interacts with the bridge superstructure, the flow field around the deck can be expressed as lines, points, and regions. The point where boundary layer detaches from the body is called a stagnation point. For objects like sharp corner rectangles, the separation point is easily considered as the sharp corner of the leading edges. The location where shear layer once again attaches to the surface of the body is called the reattachment point. The point where the flow velocity reduced to zero is called a stagnation point. Trailing side of the body after the boundary layer detaches from the body and forms a low pressure region is called a wake area. The wake area has high effect on drag magnitude. Bigger the wake area, the higher the drag magnitude. If we go deeper, the flow separation and reattachment to a submerged solid body occur when the flow abruptly leaves or return to the submerged body. The separated region produces a wake of recirculating flow on the lateral regions of the submerged solid object. The first figure here depicts the characteristic lines adopted for studying the recirculating flow within the wake region. Flow separation lines connects the zero velocity point on the velocity profile across the width of the deck on both top and bottom of the deck and separates the reverse flow in the wake region of the upstream flow. The point in the lateral region where the flow separation line reattaches to the top and bottom of the deck is called the reattachment point. Based on the vortex structure in the wake region and the understanding that vortex occurring in the girder gaps, a separation line is plotted where the velocity reverses its flow direction. The second figure shows the definition of dimensionless wake width or D star and dimensionless separation length or R star. These parameters are useful to geometrically describe the flow structure around the deck. The schematic of the flume used in this study is shown here. Dimensions of the flume was 5 meter long, 0.3 meter wide and 0.45 meter deep. The pumps could generate a peak discharge of 12.6 liter per second. The slope was adjustable from -5 to 15%. A flow straightener was installed near the inlet to stabilize the flow, and the tailgate near the outlet was used to control the flow depth. A particle image velocimetry or a PIV setup was used to visualize the flow structure around the bridge. For a PIV setup, we need a laser light, a high-speed camera, and seeding particles. In this setup, a 1000 megawatt green laser was used as the laser light. A GoPro camera having a 720 pixel resolution and 240 Hz maximum framing rate was used as the high-speed camera, and water was seeded with silver colored particles having a stroke number less than point number zero point 0.1, which means the particles followed the flow lines. For post-processing, the data collected from this setup was done using PivLab. It is a MATLAB toolbox. The best thing about PIV is it does not get affected by the flow or does not affect the flow in any way. The table here shows the test protocol followed to investigate the effect of different parameters on the flow structure around the bridge deck and the forces acting on it. The PIV images here were used to extract the velocity contours around the bridge models in order to assess the stability of streamlines around submerged decks. The streamlines were drawn from velocity vector data in the PivLab software. These figures show the progression of the flow characteristics for 4 different time steps at approaching Froude number of 0.34 and an inundation ratio of 1. At the beginning of the recording, when the time was 0.0042 seconds, which is the frame 1, streaks of streamlines were observed in this one. And after 2 seconds or 480 frames, which is in this image, the streamlines appeared to be well developed. The time average velocity contours for 5 seconds or 1200 frames and 10 seconds or 2400 frames, which are the last two images, indicate that the streamlines around the submerged deck become visible and did not show any significant difference in the velocity distribution. Therefore, for the convenience of analysis and to reduce the time required to process the images, the analysis in this study was performed for 10 seconds, which is equivalent to around 2400 frames. Flow characteristics around submerged eye-girder bridge models were investigated for two Froude numbers of 0.2 and 0.34. Although the wake region's dimensions were similar for both Froude numbers, the vortex generated on the downstream side of the deck for the lower Froude number caused a slightly increased drag force coefficient. Moreover, the differences in the length of the flow separation on the top and bottom of the deck were higher for the higher Froude number, resulting in a larger lift coefficient. Now the effect of inundation ratio. Low levels of submersion, which is A star of 0.5, did not result in vortex formations below the deck and between the girders, but vortex formations were observed for high levels of submersion, which is A star of 1 and 1.5. For A star of 1, the drag coefficient and the width of the wake were minimal. In contrast, the drag coefficient and D star were higher for A star of 0.5 and 1.5. As inundation ratio increased, the magnitude of the dimensionless separation length uh, also increased when H star was less than 1. However, the magnitude of the downward lift force coefficient reduced with the increasing inundation when the inundation ratio was more than 1. The higher negative lift coefficient at inundation ratio of 1 might be due to the greater vortex generation below the deck, which resulted in significant suction or negative pressure. The hydrodynamic force coefficients, as well as the dimensionless wake width and the separation length, increased as the blockage ratio increased. Blockage ratio affected the mean flow velocity and the flow structures more than the aspect ratio and the girder shape. As the aspect ratio increased, the drag coefficient increased, but the width of the wake remained almost unchanged. Vortex activity between the girders contributed to an increase in drag for the wider deck. The lift coefficient and the dimensionless separation length parameter or R star decreased with the higher aspect ratio. Finally, it was also found that the drag coefficient and D star were higher for I girders than box beams due to the wider flow separation. However, during the PIV experiments with the box beam, the laser sheet could not pass through the deck, limiting the ability to identify the flow region on top of the deck. And that was all from part 1. Let's start part 2. Investigation of vortex-induced scour around cylindrical piers subject to wave and current was done in this part. As mentioned before, three kinds of flow conditions were developed at the lab. Firstly, the riverine conditions where the flow is mainly one directional, means only current was present. Then coastal environments where only wave is present. And finally, the lacustrine environment where wave and current both are present. The typical scour shapes that are observed in wave-only conditions are shown in this slide. One study observed the change in scour hole shapes in wave conditions with increasing Kc or Kelugan-Carpenter number. Three types of scour hole was observed in that study with wave alone cases: twin horn shaped, transient shaped, and cone shaped. From this figure, it can be observed that with increasing Kc numbers, scour hole shape change from twin horn shape to transient shape to cone shape. For current alone cases, typical scour hole shape is inverted truncated cone around the pier. Also, the downstream deposition that occurs because of the scour looks like somewhat trapezoidal or irregular shaped. And finally, for the wave and current combined cases, the shape is similar to the current alone cases, but there are different opinions regarding the depth. It can be both greater or less than the scour depth observed with current alone conditions. One of the studies says that for these cases, the relative direction of wave and current plays an important role. The same flume as part 1 was used in this one as well to develop different conditions like wave alone or wave current combined conditions. Different features like uh, wave generator or wave absorber had to be installed in the flume. And for the PIV setup, uh, since the horizontal plane was investigated in these cases, the laser was shoot from the side. Two piers was used in this study. One was 19 millimeter in diameter and the other one was 50 millimeter. Since the plan was to observe the imprint of the investigated flow structures on a sediment bed, the sediment bed was prepared as a part of the study. You can see the schematic of the setup. It was placed in the middle at a sufficient distance away from the inlet to get a fully developed flow. Property of the sand used in study can be seen over here. Dimensions of the sediment box was uh, 1.2 meter in length, 0.3 meter in width, and depth of 5 centimeter. Pier was installed in the middle of the bed, sufficient distance away from the edges of the sediment bed, because even after providing two ramps, the gradual and smooth transition, some local scour was observed near the edge of the bed. Sediment was kept under water for 24 hours to fill the gaps between sediment particles and hydrate the soil uniformly. A total of 19 experiments were performed. On the screen, we can see the parameters for each of those experiments. Under similar flow parameters, both 19 millimeter and 50 millimeter Pier was used. Parameters like water depth and flow velocity, wave height, etc. was changed to see their effect on the flow structure and scour geometry. Now we have arrived at the result section. Before we talk about the results we obtained uh, in this section, let me talk a little bit about the complex movement associated with the waves. Because of the back and forth movement of wave, it was not possible to get fully formed vortex in waves alone and wave current combined conditions. As mentioned in part 1, it takes PIV to analyze a 10-second video to get a full vortex, but a half wave period was only 0.35 seconds. Within that time period, before any vortex formation traced, opposite flow movement disrupted the formation. During the combined wave and current cases, wave propagation direction was opposite to the current direction, which means wave induced local flow was in the direction of current when it was in trough area, which is the second image, and the opposite directions when it was in the crest area. In these current alone case experiments, fully developed vortices were observed. From multiple trials, the flow patterns and the geometry of the scour holes on both sides of the pier were observed as symmetrical, so the results of the PIV test only show half of the setup. With increasing flow velocity, strength of the vortices increased, which can be represented by the size of them. We can see that vortex size is increasing with velocity. Downstream deposition distance, scour hole size, everything increased along with the strength of vortices, justifying the effect of the vortices. By vortices, I mean the wake vortices here. To better assess the accuracy of the obtained results, samples of superimposed flow fields images onto the scour hole images are provided on top here. The horseshoe vortex is responsible for front and side of the scour hole, and wake vortices carry those dug sediment on downstream. From the table here, we can see that there is a correlation between length of vortex and flow velocity. The higher the velocity is, the stronger the vortex. A study conducted by Sumer and Fredso shows how the flow around a circular cylinder should be in an oscillatory flow at different Kelugan-Carpenter number. These two images are when wave crest is crossing the pier, meaning local flow and wave propagation are same direction, and then these two are when wave trough is crossing the pier, meaning local flow and wave propagation are at opposite directions. When local flow is at the same direction as the wave propagation, proper flow separation is observed. During the opposite flow, no vortex activity was observed. At this lower Kc value, orbital velocity is not strong enough to pick sediment from bottom. We can see that there is no regular pattern in scour. Some scour and deposition is observed here and there. With the higher Kc value, clearer vortex creation with the PIV is observed, especially in the wave propagation direction, and this flow structure is associated with a clearer pattern of scour, partially developed twin horn shaped scour, confirming the uh, findings of the previous slide. We can see from the chart that the maximum scour location at the sides of the pier and slightly downstream from the center uh, at the direction of the wave propagation. If we look at the PIV image or the one in previous slide, it is clear that vortex are being created in this region where the twin horn shaped scour was observed. Wave induced local velocity is too small to develop strong horseshoe vortex. That is why upstream or downstream scour is not observed in wave alone conditions. From the figures above, we can see that velocity vectors are at the direction of the current, meaning the flow was current dominated. That is why a similar shape of scour to current alone conditions were observed for wave and current combined cases. Since the unidirectional movement of current is disrupted every half cycle of wave, the PIV could not be used to trace the average movement of the particles and show a fully formed vortex. Wave current combined cases are complex. Since direction of wave propagation is opposite to the flow direction, when the wave crest crosses the pier, it means wave and current are at opposite direction, and when wave crest is crossing the pier, it means wave and current are at same direction. Now, when wave and current are at same direction, horseshoe vortex is created. But when wave and current are at opposite direction, there is no horseshoe vortex. To better assess the accuracy of the obtained results, samples of superimposed flow fields onto the Scour hole images are provided. Strength of wave vortices vary with the relative direction of wave and current. All these prove that although the flow was current dominated in the combined cases, the effect of waves was also significant. That is why scour depth observed in front and at the side of the piers in these combined cases were almost the same. But the downstream deposition is much gradual and smooth. Also, length of the downstream deposition is much higher than the current only cases. It is because the waves are more capable of lifting sand and the current is more capable of carrying them. Level of the wave surface from the bed level is also important. Effect of wave is less when water depth is too high, and therefore even after having higher velocity deposition length is much less with deeper flow. The PIV images are another proof of wave significance. Even though flow is current dominated, when the wave induced local flow is opposite to the current direction, which is the second image here, PIV is showing negative velocity, meaning the opposite of current movement. But this is observed for a very short period of time, otherwise the flow is fully current dominated. So through these two studies, I tried to underscore the critical role of vortex dynamics in shaping hydrodynamic loading and scour evolution. In the first study, time-resolved PIV analysis confirmed that streamlines and vortices stabilized as mean flow fields converged. For different fluid numbers, vortex behavior downstream influenced hydrodynamic forces. At the lower fluid number, the downstream vortex increased drag slightly, and at the higher fluid number, greater separation length generated higher lift. Effect of inundation ratio was also there. At lower submergence, uh, fewer vortices were produced under the deck, and at moderate submergence, uh, stronger vortices below the deck was observed, explaining the higher negative lift or suction. At the higher submergence, increased wake width and vortex intensity was observed again. Blockage and aspect ratios controlled the vortex dynamics. When the blockage ratio was higher, intensified vortex activity between girders was observed, increasing the drag coefficient and the wake width. Wider decks was uh, associated with stronger vortex induced drag. Overall, vortex formation and wake evolution were found to be primary drivers of hydrodynamic forces on submerged bridge decks. Results provide benchmark data for validating numerical vortex resolving models and demonstrate the effectiveness of low-cost PIV for flow structure studies. And in the second study for wave balloon cases, from the PIV results, flow with lower Kc values, only flow separation was observed, whereas clearer vortices were formed when the Kc value was higher. In the physical model as well, with the lower Kc values, no definite pattern of scour was observed, and for higher Kc values, partially developed twin horn shaped scour was observed. Maximum scour depths located mostly on the sides of the cylinder, and the wave induced local flow velocity is very small. It is not strong enough to create horseshoe vortices. Therefore, no scour was observed on the upstream and downstream side for wave alone cases. For the current alone cases, fully formed wave vortices were observed. Depending on the velocity of flow, location, size, and strength of the vortices varied. Strong wave vortices carried the sediment away from the pier and created small horn-shaped extensions at the tail of the deposition area. Agreeing with the PIV result, clear scour hole shape was observed in these cases, an inverted truncated cone shape around the scour hole and a roughly trapezoidal shaped deposition downstream was observed. For the waves and current combined cases, from the velocity vectors, it was observed that the relative direction of the flow was in the direction of current. That justifies the shape of scour and the deposition being similar to the current alone cases showed. The combined cases were dominated by the current component of the flow, but the wave effect was also significant. Overall, the scour depth observed in these cases was less than the current induced scour and more than the wave induced ones. So this will be all from me today. Thank you for listening to me patiently. If you're interested to know more, you are welcome to contact me via the email mentioned on the screen. Bye.